There we go. All right, so I'm here to be everyone's rah, 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 simple models. I'm here to at least push a little against that. That doesn't mean I've given up on simple models or anything, but this is a theme I've had over several ABC talks. I've talked in private with different people. I'm ready to give a little visual explanation of what I think. So my career, roughly, for those who don't know me well, I was an ABC in the 1990s. Then I spent a decade building trading software, a lot of algorithms and that. Then I was at Google for 7 years. I did a lot in advertising, online ads. I've had a lot of great talks with many Germans about what they think of that, and non-Germans. Then I did a year in cybersecurity, actually. And then I decided to move on. I'm at a small startup since March, doing consulting about AI type things. So new area for me. And across this career, I've seen indeed what ABC says. People use complex models unnecessarily and sometimes to their detriment. That is a big theme, let's say 90% of the time. But there are times when complex models are useful, and sometimes I argue they're even necessary when you end up in what I'm calling a modeling arms race. So this is the story of an example I'm going to pick to walk through how a classifier can end up getting more complex. Here's some data to classify. We have the red squares and the blue circles, and we have two cues. These don't represent squares and circles. They're supposed to represent some data. So the squares, the red squares, let's say, can be cats and the cat pictures, and the blue circles are dogs, and you need to use cues from the images to determine which is a cat and which is a dog. So here's a simple model that does it. It's linear. It's not a fast and frugal tree. I chose to focus on linear models for this talk, but a similar argument would apply to tree-based models. So this is the simplest of the linear classifiers. And suppose, though, that later, after building it, we discover an error. This one square is on the wrong side of the line. It should have been on the other side. And there's no way, even if you move the line, you can't find a way to classify it correctly. So this simple linear model ended up with an error. But it's only one of the 20 examples in this data set, which it means 95% is correct. So simple is still pretty good. And if you made a more complex model, you could get 100%. You go from 95% to 100%. That's a small difference, you can argue. And in this case, this would be an accuracy effort trade-off in this dumb, simple example. And again, an example of these would be the dogs are the red, the cats are the blues. And there is a picture out there. This is the butt of a puppy, which apparently often gets misclassified as a cat by these simple models. But you know what? I don't care if it gets the butt of a puppy wrong, because it got most of the things I care about right, so the simple model is good. Here's another example. Let's say we want to classify spam, though. Spam are the red squares. The blue circles are what's called ham, which is valid email. But now suppose that an email with the word Viagra in it, which is selling Viagra, gets through and is classified as ham by this line, but as the red square shows, it's actually spam. That would be okay, except that if the spammers keep shifting, if they shift the distribution and send more and more and more email with Viagra, people are going to start losing money, and you can end up with a really high classification error, because it's not just 1 in 20 now, because they're piling up all the errors in this one email. So that's not so good. In this case, you might actually want to go back to the complex one to deal with this distribution shift. And distribution shift, if you Google it, is a big word in these AI models and all that. The spammers don't like this. They're like, we want money, and now they're blocking our Viagra emails. So what do? You think they just retire, they give up? No. They came up with this way of fooling the classifier. They put a 1 instead of the I. So it's V1 Agra. Most humans will see that as Viagra anyway. So we're good, right? The spam goes through, the people who want to buy Viagra for them get it, but the people who don't want these emails get really annoyed and complain. And so now you need a more complex model, because we've got a lot of this. Again, it seemed like just one error, but if there's a bunch of emails there, it's going to annoy people. Just a new distribution shift, new time to complexify the model. So if you extend this argument, you end up with a super complex model to handle all the cases. I didn't draw in all the cases, I just drew in the shape. And in theory, you might have to reach sort of the full granularity limit of all the text space to get that super complex model, just to keep that spam out. But as we know, and this is not clear to everyone, but in this group, I can quickly jump to the next slide. It's hard to estimate complex models. You need a lot more data. Getting that squiggly line right is going to involve a lot of variance, and there's going to be a lot of mistakes. You're going to misclassify stuff left and right. This is a difficult problem. So the core message is, since spammers put a high distribution near the decision boundary, whatever the decision boundary is, the spam filters have to keep getting more complex. Why does this arms race happen, though? Why is it there in spam and not, let's say, in the cat and dog classification? So I'm just going to walk through some things. Basically, how the race for profit works. The first Viagra email passes those old spam filters and earns a bunch of money. Then more spam emails use Viagra, so this is a shift in the distribution. And then the spam filter builders will notice eventually and react, block Viagra, and then Viagra no longer earns profits. And so we have to move forward. Let me do this more schematically now. Same argument, same thing. The spam are the little rabbits, and the spam catchers are the foxes. This one spammer figures out how to beat the foxes. It adds this Viagra with the one. The other spammers are either going to have to do something similar, imitate it, or die out, and this one will just spend more. The other ones die out. Now that the others have died out, there's nothing for the foxes to catch anymore, and they're going to go hungry. And the one email provider who adds the more complex filter will get all the users, and everyone will stop using whatever email provider. So if Yahoo doesn't do it and Google does, Gmail does, people are going to switch to Gmail. So pretty soon the filters have to catch up too. So that's just a little argument. It's a little like coevolution. There's some coevolutionary arms races that do similar things. So the analogy is you're running to standstill. You keep changing, even though the net distance between the two, it might vary over time, but on average, it's kind of staying the same. And there's a story in Lewis Carroll about the Red Queen, where Alice has to keep running just to keep up with everyone. But no one's getting anywhere because they're all running at the same speed. So that's the analogy there. And another analogy, of course, is the arms race, where you have to build bigger weapons because the next person builds bigger weapons. Sometimes you can get avoiding building the bigger weapons. It depends. And I'm going to talk about, these are new fronts in the spam email war. There's a lot I could have talked about. I just picked two examples that are not just about a change in the distribution of the text, because I did kind of cherry pick my examples so I could show the extra complexity. It's not always like that. So one example is phishing. This is from Trusted Bank. Dear valued customer. It has the logo, it has images, it has links. And the interesting thing about this is, even though it's obvious that what Viagra was doing, when a user gets the Viagra email, they know what it's selling spam. It's spam, and you can choose to buy it or not. This fools some users. Certainly in the early days, it fooled a lot of users. And they don't know that it's spam necessarily. So that's a new way of handling it. And I say it's not just text distribution because it involves, also, first of all, the classification, the ground truth on this is unclear because users might get it wrong, and also because it's got logos and links and all this kind of stuff. It's not just the text in the email. So how is this addressed? It was not just addressed by better filtering alone. This is a sign. Basically, two things. There's more than just these two, but to simplify it, there were banks who used to send emails like this. So we had to tell those banks, don't send links with logins because this is too easy for phishers to do. So we have to teach them, don't do that anymore. Tell people, go to your bank app or whatever and go in some other way and do it that way. And then once that was all clear, we could teach users not to click on the links. There's also, hover over the link and all that kind of stuff. But basically, we change user behavior, not the filtering algorithms, because there's limits. If genuine banks are sending things like this, that's a problem. There's also, you can use external information too. You can figure out which links go to real banks and which don't. But this is kind of the core thing. You have to change user behavior, change the data itself. So in this case, this was a case of users learning new simple rules, I'd say. This was not added complexity to solve it. There's another case, this is called a vote gaming attack, that there's documented papers about how this happened in Yahoo email, although it probably happened in many other providers too. Basically, spammers made fake accounts and clicked on the not spam button, because the way that big providers know over millions of emails what's spam and what's not spam is users tell them, basically. And if a lot of people click at spam, that's how they find out. But the spammers were going in, they'd make 1 million bots and click that non-spam button. And just because 1 or 2 users click spam doesn't mean it's spam. People can accidentally click or whatever. So they were getting their emails through. It's basically muddying the ground truth. Here's these Viagra emails, but they put some votes on it that says it's not spam, and then you're not even sure how to build your classifier anymore. So again, this can't be fixed just by making a more complicated decision boundary. So what was Yahoo's response? It's the hell we've all lived through every time we want to do anything on the internet. It's these CAPTCHAs and these click on images with statues and all this. Every time you do something like create a new account or something like that, you now have to go through this hell, this extra complexity to create your account to prevent spammers from making a million bots. So in this case, it is more complexity, but not in the original filter. It's more complexity for users to log in. And there's a whole new classification problem of using the responses as human versus bot, because you can make some mistakes on those images. I know I've make mistakes in those all the time. They said, yeah, get all the traffic lights. And they're like, no, you didn't. Like, okay, you know, I messed up. There's a whole new classification problem going on. So we pushed the complexity somewhere else in this case.
Jean, you should be finishing up, please.
Yes, arms races are rare. Sometimes they're not obvious, but a key symptom was that distribution on unusually high near decision boundary. I'm going to show you one. P-values. Distribution of 3,627 p-values from this is not my data. There's a journal. I should have put the link. Sorry. 3 well-regarded psychology journals. Basically, too many p-values near the 0.05. We could replace p-values with a more complex measure. That has its downsides too, but it's basically and similar to the arms race with spammers. So that's my theme. Usually you don't need complex models, but there can be cases you get in this arms race where you have to keep up and keep ahead. Thanks. I'm done.